So let's okay. So let's say this is a normal shock. Okay, so this is say a normal shock, and I have say okay. So what I'm doing here is that I'm putting P1, rho 1, T1, U1, and so on and so forth on the other side, right? Now this is a what I'm calling as a normal shock. Okay, first things first, what exactly is a shock anyways, right? What exactly is a shock and what exactly is a normal shock? I'm saying a lot of things, and what do these subscripts denote, on each side of the normal shock. So to define or to explain or to give you some idea as to what exactly a shock is, just think of an example. Say a lot of you are traveling on your bikes. Say you are going on your bike, and in the middle of the road you see a lot of people standing, right? Now you are at a speed where you are able to see the people standing in the middle of the road. So then you ring your bell. People are able to hear you in time. They move, and you are able to avert them. And if they are able to give you way, then you go past. And say you are traveling slightly faster than that. So people really don't have a chance to move. Okay, but then when you ring your bell, they are able to see you, and you have enough time to kind of divert your way, and you are able to avert any sort of accidents, and you move past them, right? Now think of this. Now you are going at such high speed, you are riding your bike so fast that you ring your bell, but by the time the people are able to hear you, you are already there, and you are at a speed where you were not able to divert them. And whoa, what happens? You fall, you hit one of them, there is an accident, right? That's what they keep constantly telling you, drive at speeds which you are able to control. Now a shock is something like that. Okay, so let's see whether we can make some headway and understand this concept of shocks a little bit. Okay, so let's sort of visualize this cycling and hitting a couple of people a little more and see if that makes any sense to us. So let's say these are the people standing in a group, and then at some point, okay, somewhere, and then like you said, you come into the picture. You are here on the bike. Let me stop you right there. And because of you coming into the picture, you are also carrying with yourself a disturbance, right? So let's say that disturbance is shown by this halo pink sort of thing over here, and this disturbance is obviously going to travel in the atmosphere, right? So these are a group of people standing at some distance from you, and you come into the picture. You're riding on a bike, approaching them, and because of you approaching, you are also disturbing the airflow around yourself, right? And let's say that disturbance is traveling also, and the question whether we will have a shock or not is whether this disturbance will travel faster than you or slower than you. Okay, let us see what that means. Okay, so let's say let's look at this case first. So essentially the disturbance travels quicker than you, and that warns these people, right, that there is a cyclist behind itself. So the people get warned, right, they move apart, they move away, giving you way, and you are able to sort of go past without hurting anybody, without anything dramatic happening. Okay, we'll just repeat that one more time. Okay. So, we have a group of people standing here. Okay. So, just some group of people, you come into the picture. Okay. You are carrying with yourself a disturbance. The disturbance is traveling faster than you. It goes and forewarns the people. The people therefore move away, realizing that a cyclist is approaching them, right, and they give you way, and you are able to just move past, right, and that prevents any major disaster. So, essentially you can say that the source of the disturbance, which is the cyclist in this particular case, is moving slower than the disturbance. Okay, so, now let us look at this scenario again. Okay. In this case, what we will say is that the cyclist is moving quicker than the disturbance itself. Okay. So, therefore, let us see this first. So, the cyclist moves quicker than the disturbance. This is moving behind it. It goes and hits the people, right. Oops, there is an accident, all right, and well, the people do not have enough time to move away, and they really so what we get in principle out here is a shock. Okay. So, let us sort of do that again. So, we have this group of people. Okay. We have the cyclist or the source of the disturbance moving quicker than the disturbance itself. So, the people are not forewarned the cyclist is coming, right. Hence, they not able to move away. You are going and hitting those people, and hence what we have is a shock, right. So, now when I say this here, so source moving, like I said at the beginning, that the disturbance here is going to travel in the air, right, and when it travels in the air, it travels with the speed of sound. So, these two cases essentially mean that the source is either traveling faster than the speed of sound, which is it is traveling at supersonic speeds, which is this case when we have a shock, and the previous case when the source was traveling slower than the disturbance is when it is the source is traveling, or the cyclist is traveling in this particular case at subsonic speeds, right. So, this is essentially very sort of a very crude way of trying to understand what a shock wave is. Okay. So, okay, so where could this actually happen? Of course, I mean a cyclist in principle is not going to be able to travel at supersonic speed. So, what you need to visualize here is that instead of this cyclist, if you had a bullet, if you had a rocket moving at supersonic speeds, then it would be passing through the atmosphere at such high speeds that the area around that would not be able to adjust itself as quickly as this bullet is traveling, right. And then the changes would happen very quickly over a very short period of time, and that would mean that you would have a shock wave. Okay, so for example, in this picture here, so say you have this cambered airfoil out here. It's important important as to how the shape of this airfoil is. So, you can see that well this is it's a cambered airfoil, and what I have again tried to visualize here is that these are typical streamlines past the airfoil. So, just taken like 4 say particles of air, 4 pockets of air which are traveling over these streamlines. Now, I would want you to watch first what's going on. Okay. Well, let's sort of do that again. So, what I would okay, let's play that again, and then we'll talk. Well, I am hoping you have noticed here. Now, what you see is that this is a free stream. Okay, it is a free stream. It travels. Okay, it moves with the particles are moving here. Now, over this portion of the airfoil, okay, the particles actually speed up. The particles speed up. Okay, And again, just this is the around this location, which is the location of maximum camber. So, here the camber is increasing, and after this point the camber is decreasing. So, the particles come here over this increasing camber region, the particles accelerate, okay, and just as they cross, and then suddenly at around this point the camber changes from positive to negative, and the particles need to slow down again. So, they slow down just beyond this point, and then they keep moving down. Now, in this region, when the camber is suddenly changing and the flow itself also has to adjust itself, going from a faster speed to a slower speed, that is when what you get is a shock wave. So, let us say that here the flow is subsonic. It comes here in this region it is a subsonic. Now, it becomes supersonic, okay, as it speeds up, and again as it goes past this region, okay, it becomes subsonic, it slows down. So, in this therefore, so in this region, right, as it goes from supersonic to subsonic, right, and the change is really sudden, as you can see. So, in this region what you have is a shock wave. Typically this would be a normal shock wave, okay, and this, when I say normal, this normal is normal to the surface. Okay. So, now you could look at this picture a little differently as well. Okay. For example, I mean you just have a free stream, okay, you just have a free stream. Okay. Again, I just trying to visualize this flow particles, so free stream, and then suddenly you have this airfoil coming in. So, the free stream has to adjust itself, right, move past the the camber airfoil, and the way it does that is that it increases over this area, goes through a shock wave, and then goes down to subsonic. Okay. So, this is essentially again we'll just look at this one more time. So, this is essentially basically to give you a brief idea or conceptualize exactly what exactly do we mean by a shock wave. Okay. Of course, you will see a lot of Schlieren photographs and other process of visualization. So, this is something that I thought would be interesting, or a crude way to understand at least what shock waves mean or how they develop. Okay. Okay. So, let us start. Okay, let us start and do it with the okay. So, okay. So, I am hoping that you are familiar with this continuity equation, right. This is the integral form of the continuity equation. So, we will do first things first, right. We will say this is a steady state case. So, we are going to say this goes to 0. Okay. So, we are going to work with just this part. So, we are left out with this. Let us look at that equation. What is this telling us, right. We have a density, we have a velocity which is a vector, right, and this dA also. Okay. So, let me sort of rewrite this. So, I am writing this as well as dA, right. Now, I am writing the dA also with as a vector. I always thought area was a scalar, right. Why am I writing that dA with a vector sign? What does that mean? Let's sort of just do that a little bit. Now, for example, so say this is the nozzle here, right. So, say this is the okay. Now, for the entrance, the area vector always points outward. So, you have an area vector. So, that points outwards, and for this points outwards. So, area vector always point out the face or the area that always points outwards. So, this is your dA, this is your dA. Okay. And so, therefore, in this case, if I have a velocity vector which comes that way, this is my velocity, and in this case this is the exit, right. So, I have the velocity this way. Okay. So, this is the velocity vector, and that is what we, and this is what we mean by the area vector. Okay. So, now this equation actually is developed. You will remember that we use a control volume approach for that, right. So, which means, now say this is my okay, and the question to ask is, what does this mean? That we have a box and the shock wave starts from here and ends here. It is really not like that. Okay. So, what we basically are talking about is that this is a region which is kind of demarcating. There is nothing like a line or anything like that, and this is not a solid boundary anywhere. Okay. So, the way we do these things is that there is a certain space in which in a certain space which we are demarcating, where we have a very sharp change in properties, right. So, the properties as we go far away from that section are not that affected, or they are not changing dramatically. It is here that they are changing. Okay. So, so there is nothing like the shock wave stops right here. It's nothing like that. So, all I am saying is that this is the region where we have a sharp demarcation, and the properties are really changing very sharply. Okay. And there is the thing is how far or how big should be this control volume. So, therefore, this is, you have to just draw a control volume which is on your judgment, and where basically you would think that the property changes will be seen. Right. So, that is how we sort of draw up a control volume in which my property changes will show up. Right. So, if I draw up too large volume, it is probably not going to show up any show any property changes at all. So, we will take a realistic control volume and look at the property changes in this control volume. Okay. So, all right. Now, in this case, so we are talking about the area here. So, what do we go ahead and do over in this case, right? What we are going to do here is that we take this integral, right. So, we are talking about the area, right. So, say in here, if you are talking about this area, say we have just unity on the on this side. Okay, we just take unity. Okay. So, if we do that, then we are going to apply. So, we have flow coming in this way, right. This is my V here. So, this is my entrance, and this is my exit. Okay. So, in that case, so if so you can see there is this dot over here, which is essentially a dot product. Okay. So, if I had to show my area vector, so in this case for the AD face, okay, for the AD face, this is my area vector. This is my area vector, right. For the BC face, this is my area vector. For the AB face, this is the area vector. And DC face, this is the area vector. Okay. So, if that is the case, then how do we write this integral for each of these faces? Now, for AD case, how do we write this? Okay. So, say we write that as rho. Okay. So, we will write that as okay. So, let us call, say, the region before the shock as 1, right. So, that I can write all the properties in this region as rho 1, u 1, t 1, v 1, it's u 1, etc. Okay. And this is the region which is after the shock. Okay. So, if I do that, so then I write this rho 1. So, I am going to call this u 1 over here, u 1 dot say d a 1, right. This is for the AD case. Okay. So, now what is the angle between, this is a dot product, right. So, this comes up to be rho 1 So, this theta is nothing but the angle between u 1 and a 1. So, this like I said just now, so this is d a 1, right, this direction, and this is the velocity this is u 1. So, what is the angle between them? That angle is theta, right. So, as you can see, I can say that this angle is actually pi, right. So, which means that my integral comes up to so this is a negative sign over here. Okay. The negative sign comes from here. Okay. So, all we have is rho 1 u 1 the d a 1 and the negative sign. Okay. So, that is for the entrance. Okay. So, now what happens for the exit, which is the BC part. Okay. Okay. So, what happens for the BC part? So, again rho 2 u 2 d a 2, right. So, this becomes right. So, this is let us call this as theta 2, let me call this as theta 1 actually. Okay. So, if I do that, so in this case what is the theta? If you come back to this picture and see, so this is essentially, this is my u 2, actually no, this is my u 2 and this is the velocity, right. So, what is the angle between them is 0, right. So, therefore, if this angle is 0, cos 0 is 1. So, then this is what you get. Okay. So, I think that is simple to see. So, now the next question is what happens for AB? What happens to AB? Well, clearly if you do the math, you will see there, I mean there is no velocity in component in this direction anyways. So, this integral does not amount to anything for sides AB and DC, right. So, all we are left out with the contribution by the entrance and the exit, right. So, therefore, what we get is this. right. Now, for this particular case, right, now for this particular case, as you can see that the area is constant, right. So, if I may say so, because this is dA, so if I write dA1, right. So, we can take that out. So, all we are left out with is okay. So, therefore, so this is all this is the final expression that we get from the continuity equation, right. So, essentially what is happening is that the relationship between the density and velocity, this is before and after the shock. Okay. This is how they are related, and this is the relationship which we get from the continuity equation. So, the continuity equation in case of the normal shock wave boils down to this. Okay. Now, we will do the similar thing with the equation of conservation of linear momentum. Okay. So, let us do that. Okay. So, what I will do here, okay. So, let us do that, conservation of momentum. So, okay. So, this is the conservation of momentum equation. So, I hope you at least you are familiarized with this equation. So, now when we do this again, we will do the same thing as we did for the conservation of mass. We will consider a steady state case, right. So, the unsteady term goes, then this term comes for the body forces, right, like gravity, etc. So, we will take that out as well. We will just say that that goes to 0. So, what we are left out with is this expression and this expression, and then again we will do the same thing like we did for the previous case, and we will apply that, and you can see these are the area okay, area integrals. So, we will apply it over the control volume, okay, control surface rather. Okay. So, if I do that, then just AD, okay. Again let us come back and do it for the entrance. So, AD is the entrance and BC is the entrance over here. Okay. So, if I do that, so what do we get it for AD? Right. So, this is what we get. Okay. So, then if I get this, how should I write this? So, basically what we get is this, right. And so, this is let's call this term 1. So, this is term 1, right. This is say term 1, term A and term B. So, this is the term A. So, this is A. And what happens to the term B, which is the pressure, right. So, we have a negative term. So, then P into A, right. So, dA, right. Now this again here, just think about it, what should we have over here. Now, pressure, let us come back to the inlet over here, inlet and outlet. Now, by definition, pressure will always act on the surface, right. So, the pressure is always in this direction, right. So, the pressure is always this way. So, P1 will always act this way. So, in BC phase as well, the pressure will act in this way, right. So, that is always the direction of pressure. So, based on that, we will calculate the say pressure vector in terms of the area vector, right. So, here again, see if you agree with this, okay. Because for the inlet, the pressure is pointing in the direction which is opposite to that of the area vector. So, this is what we get for the second term, right. Now, for the exit, so which is the BC actually, okay. So, this is the basically for the exit. So, for the exit again, so what we have is rho 1, rho 2, right, and U2. Now, this comes up to be again, so in here the angle between U2 and dA is again 0. So, that makes it rho 2 U2 dA2 into U2. So, that is the first term, right. And what happens to the B terms? So, to the second term rather. Okay. So, that again it is P dA, right. Now, in this case, see the direction of the pressure is always opposite to that of the area vector. So, again we get the same thing. Did I say that right? Okay, let's just, okay. So, the total equation therefore boils down to so what we get is this, right. And okay, so let's write that. So, dA1 this is what we get, dA1 dA2, and as for this particular case, right. So, the area the areas all cancel out. So, we can take that out. So, what we essentially get is this, right. So, what we get is, if we rearrange a little bit, so P1 okay. So, this is what we get. So, therefore, now from the momentum equation what we are able to get is the relationship between pressure, density and the velocities, right. So, this is what the momentum equation boils down to. Okay. All right. So, we have got a little more work to do after this. So, we need to work with the energy equation, right. So, let us come up with that. Okay, so let us see. So, now we finally come up to the energy equation, right. Now, the energy equation is this. Now, again I am going to write this in full form and then okay. Okay. So, as we go further, the equations seem to get longer, right. So, I think the best thing when you look at equations is that when they are scary and they do not make any sense is not to get scared actually, because as you see here we will kind of get rid of a few terms, right, based on our assumptions. So, that will take care of the length part. So, it will become smaller. And the next thing is, once we understand what is going on here, once we understand where it came from, I think it becomes a lot easier to understand equations, because equations are not just math, they actually represent the physics. So, once we at least can understand what exactly each term means, it's slightly better. So, at this point, if you have kind of forgotten what each of these terms mean, I think it's a high time that you just go and you know, refurbish your memories, that is all. Okay, just go over it, read a very basic book and you know, find out what exactly each term means, you know, and I think to do the derivation once gives you that idea. Okay. After that, if you forget how to write this equation, which is okay, I forget it all the time, which is fine. Okay. So, here too again. So, this is the unsteady part. So, we get rid of that. Then this here is this F is the body forces. So, we will get rid of that. So, now therefore, we are left with 3 terms, right. We are left with 3 terms. So, this is the term, yeah, okay. So, that is the, so E here is the internal energy, as you can see, and so we will now denote this is the, this Q dot is the mass flux per, this is the heat flux per unit mass, right. So, we will write this for the total, we will write this, we can write this as a total for the total given mass, and we will write this as Q, sorry. Okay. So, this is what the entire equation boils down to. Okay. So, we will write this in terms of total heat flux. Okay. So, once we do that, so essentially again what we are left out with is to calculate these 2 integrals at the entrance and at the exit, right. That is what it comes down to. So, say, right. That is equal to okay. So, this equation now, if I write each of these terms for the entrance and the exit and then kind of rearrange a little bit, this is what we will get. Okay. I think it is advisable to do the same thing, you can go ahead and do it yourself. So, just write out these expressions for the entrance and exit. Okay. Just do it once and you should be able to get this, and this area I write as A. Okay. You can write that as dA if you so want. So, this is the expression. Now, okay. So, now another thing you can do here is that if I write this, if I divide now this equation by rho 1 and u 1. Okay, so, if I divide this entire equation by rho 1 and u 1. Okay, so, what will happen here is this will become P 1 by rho and this becomes rho 1 u 1 and so on and so forth. Okay. Now, there is a reason why I do that. Slowly you will see that we play around with these terms, so that all these terms start appearing in our equations. So, that is basically the reason why we do that. So, so what I am doing is I am dividing this entire equation by rho 1 u 1. Okay. If I do that, what do I get? Yeah. So, if I do that, what do I get? So, what I get is this. Okay, I get that. Okay, so this is what what we get. Do you think we can introduce another term over here? When you see these equations, do you see that I can probably introduce another term over here? What is the term for enthalpy? Right, this is the enthalpy term, right. So, how do we introduce that over here? Do you think we can do that, P into V in any case? What about this term here? Is it possible to get PV over there? Do you see if we can do that, right? Now, this is a specific volume, right? This is the internal energy per unit mass, right? Now, so therefore, here 1 by rho is nothing but V 1 actually, okay. 1 by rho here is V 1. So, therefore, I can actually write this term as the enthalpy term. So, this is nothing but H 1. Okay. So, if that is essentially H 1, you see how I get that, right. So, if I do that, then in that case, and we will let us call this as say Q. So, if I call that as Q, okay, let us write it this way. So, this part we will call as Q. Okay. So, if I do that, then this equation boils down to okay, and that is what I get from my equation of conservation of energy, right. So, therefore, I have introduced the enthalpy term here, right, and I have the velocity and the velocity. So, therefore, now what you can see from my 3 equations. So, let me write out the 3 equations, so that you have a feel for how the governing equations have boiled down to for the for a normal shock wave. Okay. So, this okay, if I go back here, okay. So, this is the equation of the second one is the equation of momentum, right, and oh. Okay, so this is the equation of continuity. This is the continuity equation. This is the conservation of momentum, and the other equation that we just derived is this. So, essentially using the 3 governing equations, what we were able to do is find out the relationship between density, velocities, pressures, enthalpy, etc. And we are able to get these 3 relationships, right. So, now using these equations, I think in the next couple of lectures what we will do is try to study the we'll do some problems and try to study the parameter changes that say a given property, or say the density and the pressure, or the pressure and temperature and the velocity in this section is known. Then if it goes through a shock wave, then what should be the changes in pressures and temperatures, etc. Now, that question is something which is not a linear question. It is not like, you know, I can just plainly say that if I make a change to the pressure in terms of say 10% pressure change, I can just say, oh, so therefore it will be, you know, 10% temperature change. No, the relationship is given by these governing equations, right. The governing equations basically define how the flow should be changing across a shock wave, right. So, these are basics of the fluid flow. So, the fluid flow, when it is changing its properties across a shock wave, will follow this rule, let us put it that way. Okay. So, therefore, we will have these equations to work with, which we will. Now, so in the next class, before we do you know, a couple of problems using this, what we will do is also find out like I said, I think in the previous class, is that what is the relationship of the speed of sound. You know, we have talked about the Mach number here as well, you know, going from subsonic to sonic, etc. So, what is the relationship of Mach number, and why are we so concerned about the speed of sound, so to speak, and what is the relationship, and does the speed of sound change along with the pressure, temperature, density, etc. Okay. So, we will find that out, you know, about the relationship of the speed of sound and Mach number, and then we will use these governing equations the way we use this for a normal shock, and we will solve a couple of problems before we go further. Okay, that should be all. Thanks.